is our actual model that we're running. I'm not going to speak too much about it because, frankly, I don't understand it. This is a great talk right here. This that I've watched a few times. Is TensorFlow and Deep Learning without a PhD. It goes through all these different operators like the convolution, ReLU, softmax, pooling, all these different sort of layers in your neural network. So what we were doing here is we had this 2D example from a sort of NVIDIA course we were at Harvard Compute Fest, where they had 2D images of hearts, and they were trying to label the ventricles. So we were kind of taking that model and just kind of extending it to 3D. So to do that, there were a few functions here that just recently, there were a few functions here that just recently got implemented for 3D. So there's the convolution 3D, the pooling 3D, and then this transpose, which is the deconvolution. So we basically took their neural network model and just extended it in another dimension. So you can see here, like the first operation is this convolutional operator. It takes as input the images that we just created. And then the weights we're going to learn for that are defined in this variable here. Okay, so the convolutional operator in 2D, you're going to have, like if you have a big image here, the convolution operator is a small window that you're going to slide over the image. And at each position, you're going to multiply the pixel value with the weight value for every element in that window, and then you're going to sum them together or something like that. Strides tells you how, so when you're sliding this window, how many steps should you skip in each dimension? So here we're striding by 2 in the x, y, and z dimensions. And then there's some other operators here. So for example, this ReLU operator, I'll show you what the ReLU function looks like. It looks like this. It's 0 if it's negative, and then it's like the line y equals x if it's positive. I don't know why that's a good thing. A lot of people have done a lot of theory, or I guess empirical research shows that this is a good operator to have. So anyway, so it's another operator, but the important thing is, so the output of the first operator gets fed in as input to the next operator, and then the whole thing kind of stacks like that. So this pool operator, the input for that is the output of the previous operator, so you've got this huge network that you're building. Here's just a little helper function, because so the interesting thing here is like all your sort of tensor shapes need to match. So that's where a lot of time is spent making sure all your sort of, the shape that comes out of one operator is the proper shape to feed into it to the next operator. So this is a little helper function that helps you debug that. So now we can actually load our images and push it through our inference function. Even though we haven't trained any weights, we can do that. Yes. Okay. So while we're building this model here, there's a lot of these little debug statements, like print tensor shape. You see that pretty much after every tensor we create. And then when you run this, you can kind of see the structure of this neural net here. So the images that get fit in are 40 by 40 by 40. Remember, this 2 is the batch size, and that 1 at the far end is the number of channels. And then we've got a 3 by 3 by 3 convolutional operator. We've got 10 of those. So now the number of channels has increased to 10. Then we've got the ReLU. It's still, so after the convolutional operator, the dimensionality drops from 40 to 20 by 20 by 20, and then it drops further down. And then eventually there's this upscore, they call it, or deconvolution, that like we end up with a pretty tiny dimensional tensor, like this convolution 4. The dimensions are, yeah, 1 by 1 by 1 by 200. And now we're kind of, so like you can think of it as a pyramid, and then we're kind of get branch back out again. So ultimately, we want our output to be the same size and shape as our input because we're labeling voxels. If we were doing like the MNIST task or something like that, where you're labeling images, the tensor shape for the output would be different. It would be like just a 10-dimensional vector, like because you're assigning one label to the entire image. But here we're assigning one label to each voxel. So we want eventually what comes out the other end. This right here is what gets returned. That should be batch size, which was 2 by 40 by 40 by 40 by 2 because we're doing a two-label problem. Blatantly stolen from an example, yeah. Yeah, this is stuff I don't really understand fully, but you know, I was hoping to get a framework, so now we can play around with this and find something. Yeah. Yes, yeah, yeah. So then we have a loss function that takes as inputs these, essentially the output of our inference function and the labels, and it's going to tell us how good we did. I think this is used to calculate the gradients. If anyone knows a little more about machine learning than me, you compare the results you get to the results you want so that you can compute the gradients and update all your weights. Okay, so then we can start the training. So the training takes as input this loss, the difference between the current state of the network and the ideal state of the network, and then all these things like learning rate, decay steps, and decay rate that I don't fully understand yet. So we're using an exponential decay, and then we're doing gradient descent, and then we want to minimize loss over, you know, our training set. This is like a little helper function. So when we went to this course, there was this thing called TensorBoard, which was pretty cool. So you could like run a network, and then it would pipe data through some feed, like something was harvesting the log files and generating all these nice, pretty plots, so you could actually see what's happening to your loss function. You can see like how things were getting trained. We didn't get that up and running yet, but all this functionality is here. I think these summary statements are kind of summarizing things for TensorBoard. Yeah, and there's some like checkpointing here. So after like 100 iterations, it's going to save it's going to print out some info and save like a little checkpoint file. And then here's the go button. So I would strongly suggest you save your work before running this. It will probably crash your computer. But yeah, that should actually, okay, let me go through and run all the steps in my notebook here. Oh, okay. And you get the same thing? Okay, thanks. Okay. Sorry? Oh, yeah, so you need to import time and then change exactly what Chris posted here, yeah. So here it is. So now I'm getting these like checkpoint files written to my notebook. I think it's still running. Yeah, it's definitely running because my CPU is still at. And that's as far as we got. So we can get it to train. Um, I guess the next step would be to write an evaluation function to see how well uh, the training does. Um, yeah. Any questions? Yeah, I mean, I'd like to be working on it. I mean, I don't think it'll be just like a hobby project of mine, so I don't know how much time I'll have to it, but I would love to keep working on it and get a fully working sort of 3D example. Uh, cool. And port this to C++ because the Free Surfer Lab is all about C++ and they're itching to play around and stuff like that. So I know there is a C++ API, but I suspect that will be an effort. John, do you have a good sense of that? Is it running for everybody else, or are they getting errors, or that? Um, and eventually you should get some of these print statements here. I guess one thing we could try is changing this just so it's a little more verbose. If I change this to like, so this is also threaded, and I don't know how threads work with Jupyter. Does anyone know if, because I think this is actually starting two threads, so I don't know if I hit the stop button, if does that stop all my threads? I'm okay with that. Okay. Now this should print out something every loop. So let's see what happens. not getting anything. So I don't know how long these loops take. Yeah, yeah. You remember, Monica? 200 and some, yeah. It seemed to work reasonably well. It was these 2D images, and I don't remember how big they were. Were they 256 by 256? Um, yeah, one slice, yeah. Yeah, tens of thousands, I would expect. Yeah, yeah. Uh-huh. Yeah, right. So it's like a filter bank. You're starting with like, yeah. Oh, that's interesting. Right, right. Response to the features, yeah. That's interesting. They have that for like 3D filters or just? Yeah, yeah, yeah. Yeah, 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 yeah. It would be a fun project to try and get like every freely available T1 we could find, right? And then push it through something like that and get like, yeah, yeah, yeah. Yeah, that's interesting. I think that's what you were talking about yesterday, right, Satra? Like with that's like something Keras supports. So maybe we should have done all this in Keras. I don't know. Like it's a little higher level. I guess it sits on top of TensorFlow, and it makes managing your network and stuff a lot easier. Um, I was kind of skeptical because I know the 3D operators are so new, right? Like I don't know if they're in Keras yet or if they're supported. They are, eh? Okay, all right. Yeah, absolutely. I think Keras definitely makes this inference function a lot easier to write because managing all these little dimensions and stuff is tricky, you know. Yeah, he was at that thing in Mountain View. Yeah, right, right, right. Which is probably the way to go. But this was a good learning experience. Like now, I think when I go to the higher level, I'll have a better appreciation for all the things it's abstracting for me, right? And a better idea of what's going on and like under the hood. So, yeah, is anyone getting output from this? I still don't have any output. But probably slow. Stop that. Um, this is like a threaded app too. So what you're actually starting is multi-threaded. So then things get. Where do the threads actually get initialized here? Yes. Oh yes, yeah, I can. I'll do that when I sit down. Um, yeah, yeah. Thanks, guys. Thanks to MIT for organizing this. It was a lot of fun.